This is 2014, question 4. Based on this, it's looking like a little bit of Riemann's sum as well as particle motion. So let's get to it. Here's part A. We want to find the average acceleration. Okay, so average acceleration is pretty much them asking you for the average rate of change to estimate A of whatever, okay? Another way to do that is to find the average rate of change of V of 8 minus V of 2 all over 8 minus 2. Okay, this is the same thing as you finding the average rate of change. So here they provided us these values. V of 8 is really just negative 120. V of 2 is just really 100. And that's enough to leave it as equals equal. They don't ask for units, so you can actually just leave it just like this here. Here's part B. The data in the table, they want to know if it's possible for the velocity to come out to 100 meters per minute. Okay, so we want to know, is it possible somewhere in between 5 and 8 such that the velocity comes out to negative 100. So this is only going to be possible if the function is continuous. And if you notice here, they mentioned that it's differentiable, so that implies that the function is also continuous. So since the function is continuous, if you go from 40 and then you end up at negative 120, there has to be a moment where you have to pass negative 100 according to the intermediate value theorem. Okay, here's part C. At t equals 2, train A's position is 300 meters east of the origin station, and the train is moving to the east. Write an expression involving the position of train A at t equals 12. So here's what you do. We want to know the position at 12. So you have to integrate V somehow so that you can go back to displacement or distance or whatever you want to talk about here, okay? So the trick here is knowing what the bounds should be. So if you want to know your position at 12, that's where you should end it. Okay, now where do we start? You're going to start at whatever value they give you. So in this case, it's t equals 2. So this just tells you your movement, how much you moved, but they didn't tell you where you started. So what you have to do is you have to consider what your position is at t equals 2, which in this case is 300. Okay, so if you set it up like this, you should be able to write that expression. Then they ask you to use a trapezoidal sum to approximate the position. So here we have 300 plus that integral. So in order to get that integral, we're going to use the trapezoid approximation here. So here we go. It will be 1/2 times the horizontal distance between 2 and 5, which in this case is 3, times the sum of the two bases, 100 plus 40. I'll do one more, plus 1/2 times the horizontal distance, which is 3 again, times the sum of the two bases. And I don't have enough room, but you could do the rest right there. And that's pretty much it. Okay, here's the last part. They introduce a second train, train B, which is going north, okay, from origin station. So origin station just means from 0, 0. At time t, they have this velocity model here for train B, and they tell you at time 2, the train is 400 meters north of the station. So the trick here is you actually have to draw this one out, and I'll draw it out over here. Train B is heading north, okay? Train A is actually heading east. So we want to find the rate, so we know it's going to be a derivative, at which the distance between train A and train B is changing. So before we get to the rate, take a look at this phrase here, okay? The distance between train A and train B. So however far train B went or train A went, this black dotted line here is going to represent the distance between the two trains. Okay? So now that we're factoring in two different rates, we have to see how they're related. Okay? Notice how that makes a right triangle since they're going north and east respectively. We have to come up with an equation that relates all of those sides there. Okay? So I'll call this x, y, and z. We could use the Pythagorean Theorem to show that all of these rates are related. So if you happen to take the derivative, let me speed it up here, you should get this right here, 2z with respect to z dt, 2x with respect to x dt, and 2y dy dt. Okay? So then what you're going to do is you're going to plug in pretty much everything that you know. So here, we know that at t equals 2, the horizontal distance, or the distance of train A, is going to be 300. They mention it right here in part C. So I know that this right here is going to be 300. And to find y, you can actually just plug in t equals 2 here, or they tell you right there. Train B is 400 meters. So the last one here is finding out what train Z is. You could actually use the Pythagorean Theorem to find out that Z will come out to 500. Okay, so if we plug all those in, we'll be able to have those values. So the only thing we're missing here is dz dt, which is the rate at which the distance between train A and train B is changing. Okay, so that's actually what we're looking for here, okay? So all we need is dx dt and dy dt. dx dt is the velocity of train A. The velocity of train A at t equals 2 is 100. So I could actually plug in 100 there. Now the velocity, dy dt, the velocity of train B is given by this equation here. Okay? At t equals 2, if you plugged in 2 here for t and you solve it out, you should get 125. Okay? So pretty much now we have every variable figured out except for dz dt. All you have to do is isolate it and pretty much equals equal there. Okay, and they don't ask for units, so you're pretty much set.